Okay, so think of this like a detective story, but instead of a detective, we've got a computer. And instead of clues, we've got data. That's what we're diving in today. We're going to teach a computer how to be a pumpkin detective, how to look at a bunch of facts about a pumpkin and predict its color. It's all about cracking the code. So here's the big question, right? We've got this file just packed with pumpkin facts. You know, its size, its variety, where it came from. How in the world do we get a machine to sift through all of that and make a really simple prediction? Is this pumpkin orange or is it white? All right, so this is our quest. We're going to take a raw file of pumpkin stats and get it totally prepped for an AI. That means we have to clean it, organize it, and basically translate it into a language the computer can actually understand. The end goal? We want to feed this data into something called a logistic regression model. Now that sounds super technical, but it's really just a fancy name for a type of AI that's awesome at sorting things into one of two buckets. And the key thing here is what we're asking the computer to do. We're not asking for a number, like, hey, how much does this pumpkin weigh? Nope. We're asking it to pick a category. Is it orange or is it white? This is what's known as a classification problem, and it's exactly the kind of job that logistic regression was built for. You know, any good detective will tell you the first step is always to organize the evidence. And for us, well, that means we've got to get our hands dirty with the raw data. We have to clean this stuff up before we can even think about making any predictions. So let's open up the case file and see what we've got. Okay, so here it is, our initial evidence file. And yeah, it's a bit of a mess. You can see there are columns for all kinds of information. To solve this thing, we really need a focus. So our first job is to cut right through all this noise and only hang on to the clues that are actually going to help us predict a pumpkin's color. And we're going to do this in two really simple steps. First, we're just going to keep the columns we think we need: city, variety, origin, item size, and of course, the color. Everything else? Gone. Second, we're going to look for any rows that have missing information and just drop them. What we're left with is a clean, tight, workable data set to really start our investigation. So as soon as we visualize this data, a huge clue just jumps right off the page. Look at that! The vast majority of our pumpkins are orange. This imbalance has a name. It's called skewed data, and it can be a real problem for our model. I mean, think about it. If the AI mostly sees orange pumpkins, it might just get lazy and learn to guess orange every single time. So we've got to keep this bias in mind as we go. Okay, so we've organized our clues, things are looking good, but now we've hit our biggest obstacle, a real roadblock. It's a fundamental problem that we have to solve, otherwise we can't go any further. And it's basically a language barrier. Our computer just doesn't speak the same language we do. And this is the heart of the issue. Our data is full of words, or strings as they're called in programming, like Boston or PyType. But our AI, the brain of this whole operation, is basically a mathematician. It doesn't understand English. It only understands numbers. So guess what? We have to be the translator. Now, there's a technical term for this kind of data, and it's categorical features. All that means is that the data sorts things into, well, categories, like a city or a size, instead of just using plain old numbers. So our next mission is crystal clear. We have to translate every single one of these categories into a number. So how are we going to pull this off? Well, this is the fun part. This is where we become code breakers. We're going to use a couple of really clever techniques to translate all this text data into the pure language of numbers. We're finally going to bridge that communication gap with our machine. So take a look. Here's our challenge right in front of us. We've got text in the item size column, and we've got text in the city column. Now you might think, hey, just translate them the same way. But nope. There's a really crucial difference between these two that means we need two totally different code-breaking techniques. And this is the critical distinction. On the one hand, you have data with a natural order. It just makes sense to rank small, then medium, then large. But then you have unordered data, like cities. There's no logical order there. I mean, if we just assigned Boston the number 1 and Atlanta the number 2, the model would think that Atlanta is somehow greater than or more than Boston, which is totally meaningless, right? And that's exactly why we need two different tools for these two different kinds of text. Okay, so for our ordered data, like item size, we use a method called ordinal encoding, and it is beautifully simple. We just assign a number to each category based on its rank. So small becomes 0, medium becomes 1, large becomes 2, and so on.
See, we're just turning a logical sequence of words into a logical sequence of numbers. Easy. But for that unordered data, like the city names, we need a much cleverer tool. It's called one-hot encoding. And instead of ranking anything, what it does is it takes that single city column and explodes it into multiple new columns, one for every single city in our dataset. Then, for each pumpkin, it just goes down the list and puts a 1 in the column for the city it's from and a 0 everywhere else. It's basically like creating a super detailed checklist that the computer can read perfectly. Brilliant. And here is the after, the big reveal. Just look at this. The item size column is now all numbers, 0, 1, 2. That's our ordinal encoding at work. And check it out. The original city column is totally gone. It's been replaced by all these new columns like city_Boston, city_New York. That first row has a 1 right under Boston, which tells the computer, yep, this pumpkin is from Boston. That is one-hot encoding in action. I think it's safe to say the code is officially cracked. All right, our evidence file is now perfectly translated, perfectly organized. We are on the final step before we can hand this entire case over to our AI detective. There is just one last little piece of text we need to translate, and it's the most important one. It's the color column, the very thing we're trying to predict. But this one's super simple. We'll just map white to the number 0 and orange to the number 1. Done. And with that final piece in place, I think our data is in pretty good shape. It's clean, it's all numbers, it's perfectly structured, the evidence is prepared, and the case file is ready for our model. So let's recap. We've taken our entire case file and translated it perfectly into the language of numbers. But this brings us to the biggest question of all, doesn't it? How does a machine actually look at this giant grid of 1s and 0s and learn from it? How does it find the hidden patterns it needs to predict a pumpkin's color? Well, that's the next step in our quest. And trust me, that's where the real magic begins.